Hello, this is the Section 5.6b lesson. Section 5.6a, we talked about the two-sample t-test, which was used to compare means from two independent populations. That requirement of independence was very, very important. What we're going to talk about in this section is a test that we can use to compare two dependent populations. This test is called the paired t-test. So to illustrate this test, let's look at example 563. At a large university, freshman students are required to take an introduction to writing class. Now in this particular class, students are given a survey on their attitudes toward writing at the beginning of the class and at the end of the class. And each student receives a score between 0 and 100 on both their beginning test and the end test. And so a large score indicates that they have more favorable attitudes towards writing. A small score means the opposite. And so what we want to do here is look at do scores improve overall, or do they decrease overall, or what's going on? We're going to look at some data here in a minute, but specifically we're going to test the claim that scores improve from beginning to end. Now here's the data that we're going to use. And so what we have here is we have randomly selected 9 students from this class, and we have recorded their beginning score and their end score. So like this student here got a score of 77.6 at the beginning and a score of 85.4 at the end. So this student's scores improved from beginning to end. The second student started off with a score of about 86 and ended with a score of 83. So that student did not increase. Notice some of these scores are rather large at the beginning and at the end. Some of them are rather small at the beginning and at the end. And so if we just kind of take a quick look at this data, it looks like most students improved from beginning to end. And now at first glance it looks like this is a problem from section 5.6a. We've got two populations. So we've got a population of scores at the beginning and a population of scores at the end, and we want to compare them. So this looks like a simple two-sample t-test like we did in section 5.6a. However, let's make some very important observations about this data. First observation is that these data come in matched pairs, meaning that each student gave us two numbers, a number at the beginning and a number at the end. This number here is matched up with this number. This number is matched with this number. This number is matched with this number, so on and so forth. So the data come in matched pairs. So what does that mean? Well, that means that these two populations, the beginning scores and the end scores, are not independent. Remember, independence means that what happens to one population has no effect to the other population. However, note that if a student's beginning score is large, like for this student right here, then their ending score is probably also very large. Now, that doesn't mean that they're identical, but a big number here indicates probably a big number down here. Likewise, a small number at the beginning indicates that we're probably going to have a relatively small number at the end as well. And so what happens to one population does have an effect on the other population. So these two populations are not independent. So that means that we have not met the requirements for the two-sample t-test, so we cannot use that two-sample t-test from section 5.6a. Looks like we could. We got two populations. We want to compare them, but this requirement of independence is not met. So we're going to have to do something else. What is that something else? Well, let's make another observation here, is that if the scores really were to improve, then the differences of end minus beginning would be positive. And so here in the third row of our table, we have calculated these differences end minus beginning. For this first student, the difference was 7.8. A positive difference here indicates that the score improved from beginning to end. The second student, the difference was negative 2.9. That negative number indicates that that student's scores decreased. And so if we just glance at these differences here, notice that most of them are positive, and we have only 2 of them that are negative. So scores, these differences are positive, or most of them are positive, which indicates that scores really do improve. Okay? So now, if most of those differences are positive, well, that would mean that the mean of these differences would be positive. Right? If we added up all of these differences and divided by the number of differences, that result would probably be positive. And so what we're going to do here is restate our claim in terms of the mean of these differences. So we're going to test the claim that the mean of these differences for all students is positive. And so that's going to be an equivalent way of stating our claim. The original claim was that scores tend to improve. In more formal terms, we're going to test the claim that the mean of these differences for all students is positive. And notice here that we use this word all here because we're interested in the large population of all students, not just the 9 students in our sample. Okay. So let's start setting up our hypothesis test. We'll talk about the details here in a minute, but the first step in any hypothesis test is to define the parameter. So the parameter that we're going to use here, we're going to denote mu sub d, and it equals the mean difference of n minus beginning of all students. Now, this is denoted mu sub d. Mu denotes a population mean, and that's really what we're dealing with here. It's the mean of a single population. Here our population is all students, and it's denoted mu sub d. The d indicates that this is the mean of a difference. So don't let that notation mu sub d scare you. It just indicates that it's the mean of some differences. Now our claim in mathematical notation is that mu sub d is positive. And so our hypotheses that we're going to test are: the null is that mu sub d equals 0. This is like a status quo, what we would expect to happen if we didn't have any data to indicate otherwise. We might suspect that this class had no effect on scores, and so that would mean that these differences would all be 0, which means that their mean would be 0. So that's our null hypothesis. Our alternative hypothesis, the statement that's suggested by the data, is that mu sub d is greater than 0. So there's our null and alternative hypotheses. The second step in hypothesis test is to calculate the test statistic. And so let's talk about how we're doing this here. So the test we're using is called the paired t-test, and the purpose is to test a claim that a set of paired data come from a population in which the differences have a mean less than, greater than, or equal to 0. And that's exactly what we have here. We have data that comes in pairs. Each student gives us 2 numbers. And we're testing, and the claim is that these differences have a mean that's greater than 0. Okay? So the first step is to let mu sub d, that's our parameter, denote the population mean of the differences. We've already defined that. The null hypothesis is the statement that mu sub d equals 0. That's exactly what we have here. The third step is to calculate these differences, which we've already done. And then the fourth step is to use these differences from step 3 and a t-test from section 5.3 to test the claim. And so let's briefly review the t-test. The t-test, the purpose of a t-test is to test a claim about the mean of a single population. And in the end, that's really what we're doing. We have this population of all students and the differences in the scores for all those students. We're testing a claim about the mean of that population of differences. And so in the t-test, we have a null hypothesis that looks something like this. Mu equals mu naught. Mu naught is some number. Mu is our population mean. Now here in this particular example, our mean is denoted mu sub d, but that's that mu sub d is just the mean of a single population. And so we go out, we collect a sample from our population. In this case, we're going to collect a sample of differences, which we've already done. We need to calculate the sample mean and standard deviation and sample size. And then here is our formula for the test statistic. And then once we did that, our critical value was a t-value with n minus 1 degrees of freedom, which came from table C3. Our p-value is an area underneath a student t density curve with n minus 1 degrees of freedom. Okay? So in the end, we're going to be doing a t-test just like we did back in section 5.3. Now, real quickly, let's talk about the requirements for this paired t-test, then we'll start applying it to our example. First requirement for this paired t-test is that the data come in matched pairs from two measurements. And that's exactly what we have here. Our measurements are the score at the beginning and the score at the end. Our data come in matched pairs. So our first requirement is met. Number two, the data are randomly selected. That's always a requirement. And then third is that the differences come from a population that's normally distributed, or n is bigger than 30. Now in this case, n is only 9, so we don't meet this part of the requirement. And so we're going to assume that our differences have a normal distribution. Okay. All right, so let's get back to our example. The first step in hypothesis testing was to define the parameter, which we did already, and we stated our null and alternative hypotheses. The next step was to calculate our test statistic using the formulas from the t-test. And so what we have here in our last row is our sample of differences. So once we've calculated our sample of differences, that's really all we need to work with. We don't need to work with these beginning and ending scores anymore, because we're only really interested in these differences. And so in order to apply the t-test to those differences, we need to calculate the mean and the standard deviation of those differences. And here's the results. Now we'll verify these numbers here in a bit on our calculator. There's our mean difference. Notice that it's positive, as we expect. Here's our standard deviation. And so now we calculate our test statistic using our formula. Here's our sample mean. Here's mu naught, 0. That's this number right there, over standard deviation divided by square of the sample size. And so there's our test statistic, 2.32. The third step is to find our critical value, or find the p-value. Now we're going to use the default 0.05 significance level because no significance level was given. So our critical value is this t-score with 8 degrees of freedom. You can look that up from our table. It's 1.860. The p-value is the area to the right of our test statistic. This is a right-tailed test, so it's the area underneath the student t-density curve with 8 degrees of freedom. And we'll verify this here in a minute, that p-value comes out to be 0.025. Fourth step is to come to our technical conclusion. So here's our critical region. Here's our p-value. Now notice that our test statistic is in that critical region. Also note that the p-value is very small, less than 0.05, and so using either method, our technical conclusion would be to reject the null hypothesis. The last step is to state our final conclusion. The original claim did not contain equality, and so our final conclusion is that the data indeed support the claim. What that means in even less technical terms is that our scores do appear to increase on average. Doesn't mean that every score increases. We already saw that from the data, but it looks like on average scores do appear to increase. Now lastly, let's talk about how we can do all these calculations on the calculator. Now in a paired t-test, what we're typically given is just the beginning scores and the ending scores, those raw scores. And then from there, we're going to have to calculate the differences and apply the t-test to those differences. So the first thing we need to do is to enter our beginning and ending scores into the calculator. So go to the Stat menu and then edit so that we get our lists of data. And in L1, we're going to enter the beginning scores, and in L2, we're going to enter the ending scores. And the next thing we need to do is calculate these differences, and we're going to store those in list L3. And so what we're going to do is first highlight the name of that list L3, and then we're going to enter this command down here, L2 minus L1. Remember, L2 is our ending scores, L1 is the beginning score. So you can select L2 by pressing second 2, and then L1 is second 1. So you do L2 minus L1, and then you hit enter. And when you do that, it will calculate the differences for each student. And so here's our differences. And so now we're going to use this sample of differences and our t-test. So next step is to go to a Stat menu, Tests, choose option 2 for the t-test, and you're going to get a window that looks something like this. So the first thing we have to do is select how we're going to input our information, either data or statistics. Now, in this case, we have raw data. List L3 contains raw data of our sample of differences. And so we're going to choose Input Data. Next thing is we're going to input L or mu naught, which is the mean used in the null hypothesis, which is 0 in this case. And the next thing we enter is the list containing our raw data. Our raw differences are in L3, so we're going to select L3. Frequency is always the default 1. Next, we enter the form of our alternative hypothesis. And our alternative hypothesis was that mu naught is greater than 0, so we're going to choose this last option. And then choose either calculate or draw. Let's select calculate and press enter. And we should get a window that looks like this. As always, the first row tells us the test that we did. The second row tells us our alternative hypothesis as we entered it. We see that's exactly what we want. The next row gives us our test statistic, 2.32, which is exactly the same thing we got by hand. Next is the p-value, which is for our purposes the most important number. And then here it gives us the mean of our differences, of our sample of differences, the standard deviation of those differences, and our sample size. Okay. So these numbers here aren't terribly important. That just gives us our sample statistics. So right there, the p-value, that's our most important number. Notice that p-value is small, 0.025, less than our significance level of 0.05. So that would cause us to reject the null hypothesis. So there we go. That's all there is to doing the paired t-test on the calculator.